This is my lab report for Lab 4 about Faraday's Law. The purpose of this lab was to observe a magnet falling through an aluminum cylinder, construct a computational model of the magnet falling, and understand applications of Faraday's Law. The physics principles used are Faraday's Law, which relates voltage and the derivative of flux, magnetic flux, which is the amount of magnetic field perpendicular to area, and Lenz's Law, which states that induced electric current creates a B field opposite to the change in flux. For the results of the experiment, we got that the magnet took 1.27 seconds to fall through the aluminum tube, and the computational model predicted that it take 1.133 seconds. For the lab setup, the length of the aluminum tube was 0.3 meters, the width of the foil was 0.005 meters, and the inner radius of the foil was 0.032 meters. The magnetic moment, which was calculated back in Lab 3, was found to be 2.7, and the mass of the magnet is 0.022 kilograms. And when we drop the magnet through the cylinder 5 times, we get the average time taken to be 1.27 seconds. For the glow script model to model this scenario, we first need to set up the initial conditions where we input the length of the tube, the width of the foil, the inner radius of the tube, and the radius. So then we use the Biot-Savart law to calculate the dipole, the magnetic field due to the dipole, and we use this using this function. And then we calculate the flux due to the magnetic field of a series of rings that we can model the aluminum foil as. Our next step is to calculate the ring current, where we use Lenz's law, which states that the change in flux is opposite direction to the current. And then we calculate the typical B field at each ring, and we do this by taking the B field of the dipole of each ring, and then since it's a tube, we use calculate the flux and the force at each ring, and that iterates throughout. And then we calculate the magnetic force, and then we calculate the gravitational force, and since they're acting in opposite directions, we need to calculate the net force. And then we use the net force to update the position and velocity vectors. For the computational results, we get that the velocity time graph is shaped like this curve, and we find that the time in the tube is 1.133 seconds, which is similar to what we got in our experiment, so we know our computational model is fairly accurate. For the discussion questions, what if the resistivity of the conductor were reduced as close to possible as 0? How would the dynamics of the following magnet change? So due to Ohm's law, this would cause the induced current to be much greater, as well as the time it takes for the magnet to fall. So what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So the model would have fewer rings, which would cause the induced current and magnetic field to be smaller, and it would take less time for the magnet to fall through the tube.